You know how we often use the word shock pretty casually, like I was in shock when I saw that bill.
Yeah, just meaning surprised, right?
Exactly, just a stand-in for surprise. But in medicine, shock describes something profoundly different, an incredibly dangerous state for the body.
Yeah, absolutely.
So today, we're doing a deep dive into the syndrome of shock, physiology and pathophysiology, and we're drawing from an expert medical text. Our mission really is to unpack well, the intricate ways the body responds when its fundamental ability to get oxygen and nutrients to its cells is compromised.
Yeah, that delivery system.
Right. We're going to explore what shock truly means medically, how it hits the body right down at the cellular level, and, the complex, sometimes desperate mechanisms the body uses to try and survive.
Exactly. And at its core, shock isn't really one single disease. It's what we call a clinical syndrome. It results from inadequate tissue perfusion.
Okay, perfusion. So getting blood flow to the tissues.
Precisely. Think of it like the body's delivery system for oxygen and nutrients just isn't meeting the demands of the cells. And for that system to work, you need, well, basically 3 key things working together. An effective cardiac pump.
The heart needs to be working well.
Right. A strong pump. Then you need an adequate vasculature, the circulatory system, the pipes have to be intact. And finally, sufficient blood volume. Enough fluid in the pipes, if any one of those falters, that vital tissue perfusion is threatened. And the consequences, well, they can be really dire.
And the text really drives home that devastating cascade that follows, right?
Yeah.
It says poor delivery of oxygen and nutrients, which leads to cellular hypoxia.
Cell suffocating, essentially.
Basically starving for oxygen. And then that progresses to cell death that progresses to organ dysfunction and eventually death. It's not like a real race against time for the body.
It absolutely is.
So when we talk about shock, you mentioned the syndrome. Does that mean it hits just one specific spot, or is it broader, like a whole body crisis?
Oh, it's definitely a systemic crisis. The source points out that shock affects all body systems. It's not localized. It's a widespread issue. And it can develop, really rapidly or sometimes more slowly depending on what caused it.
What kind of things can cause it?
Well, what's fascinating and kind of scary is that the text says any insult to the body, like a severe infection, major trauma, a heart attack, any of these can trigger this cascade leading to poor tissue perfusion.
Wow, so pretty much anything serious.
Yeah, it means, and I quote, any patient with any disease state may be at risk for developing shock. Now, we do classify shock based on the underlying problem, like hypovolemic shock from losing fluid.
Like bleeding out or dehydration.
Exactly. Or cardiogenic, where the heart pump itself fails. Obstructive, where something physically blocks blood flow. And then there are distributive shocks, septic shock from infection, neurogenic from nerve damage, anaphylactic from allergic reactions.
Okay, so different triggers, but does the body react in the same way generally? Is there like a common playbook it tries to run?
That's a great question. Yes, absolutely. Regardless of the initial cause, there are these common physiological responses. You see hypoperfusion of tissues. Not enough blood getting through.
Okay.
You see hypermetabolism. The body's engine revs way, way up, trying desperately to compensate.
Trying to make energy.
Trying to meet the demands, yeah. And there's this general activation of the inflammatory response. Plus, the body immediately hits the panic button, activating the sympathetic nervous system.
Fight or flight.
Exactly, that classic fight or flight response. But here's the critical point, the often tragic turning point. The text says, failure of compensatory mechanisms to effectively restore physiologic balance is the final pathway of all shock states and results in end organ dysfunction and death.
So the body tries to compensate. But if those efforts fail, that's when things really go downhill.
That's the cliff edge, yes.
And knowing that, the failure of compensatory mechanisms leads to organ dysfunction and death. I mean, recognizing the early signs must be absolutely critical. Life or death, literally. Especially for doctors, nurses.
Precisely. The text specifically highlights that nurses are in key positions to identify early signs of shock and anticipate rapid therapy. But it's not a solo job. It absolutely requires close collaboration with other members of the healthcare team to jump in quickly and give the patient the best possible chance.
Okay, so we've kind of mapped out the body's big battle plan against shock.
Yeah.
But you mentioned the real front line, the actual struggle is much smaller, right? Deep inside ourselves.
That's right.
So let's zoom in. How do our cells normally get their energy? What's the standard process?
Okay, so at the most basic level, cells run on energy currency called adenosine triphosphate, or ATP. They make it through energy metabolism, breaking down nutrients.
ATP, that's like the fuel molecule.
Exactly. It powers pretty much everything a cell does.
Yeah.
Now, ideally, cells make ATP with oxygen. That's aerobic metabolism. It's super efficient, like a clean burning engine, gets you a lot of ATP.
Okay, high yield.
Very high yield. But when oxygen isn't available, like in shock, cells are forced into this emergency backup mode, anaerobic metabolism, without oxygen.
And that's less good.
Much less good. It's like a sputtering, dirty generator. It produces way less ATP, and worse, it creates a toxic byproduct, lactic acid. And that lactic acid then has to be dealt with, usually by the liver, which takes more energy.
So the cells are starved for oxygen. They flip to this inefficient, messy backup generator. What does that do to the cell itself physically?
Yeah, great question. So being deprived of oxygen and nutrients, they're stuck in anaerobic metabolism. This means low energy yields and, really importantly, an acidotic intracellular environment. Things get acidic inside the cell.
Okay, that can't be good.
It's definitely not. Normal functions just start to break down. Physically, the cell actually starts to swell up. Its outer membrane becomes more permeable, kind of leaky.
Leaky.
Yeah, electrolytes and fluids start seeping out, and unwanted stuff seeps in. The really vital sodium-potassium pump, which keeps everything in balance, gets impaired because it needs ATP, which is now scarce. And then cell structures, especially the mitochondria.
The powerhouses.
Right, the powerhouses, they get damaged. And ultimately, if this goes on, it leads to the death of the cell.
Wow. And while all this chaos is happening inside the cell, the body's wider stress response is kicking in, right? Trying to help, but you hinted it might cause its own problems, like a double-edged sword.
That's a perfect analogy, yeah. In these extreme stress states, the body just floods itself with hormones and signals, catecholamines, things like adrenaline, plus cortisol, glucagon, and various inflammatory cytokines.
Alarm bells going off everywhere.
Exactly, biochemical alarm signals. And a major effect is causing hyperglycemia, high blood sugar, and insulin resistance. It's trying desperately to mobilize every scrap of glucose for the cells to use, even if they can't use it efficiently without oxygen.
How does it mobilize glucose?
It triggers processes like gluconeogenesis that's literally making new glucose from non-carb sources like proteins and fats.
Breaking down muscle and fat for sugar.
Essentially, yes. And also glycogenolysis, breaking down stored glycogen, mostly in the liver, into glucose. Both pathways dump glucose into the blood, trying to meet those massively increased metabolic needs of the hypermetabolic state.
But you said this could become a negative cycle. How does that happen?
Well, the problem is this continued activation of the stress response by shock states causes a depletion of glycogen stores. You run out of the easy access reserves.
Okay.
So the body doubles down on increased proteolysis, breaking down more protein, muscle tissue, essentially. And this, combined with the cell death, contributes to organ failure. You also get this buildup of metabolic end products, waste inside the cells.
And there's something else, clotting.
Yes. Complicating everything further is the clotting cascade. It's linked to the inflammatory response, which is already activated. Normally, clotting stops bleeding, right?
Right.
But in shock, the system can become overproductive. It starts forming tiny, small clots lodging in microcirculation, the smallest blood vessels.
Oh, no. So it blocks the tiny vessels.
Exactly, which further hinders blood flow and oxygen delivery to tissues that are already struggling. It creates this vicious cycle, a self-perpetuating negative situation. We actually call it a positive feedback loop in physiology, where the response makes the initial problem worse.
Wow. So the body's attempt to control bleeding can actually worsen the perfusion problem.
It's a tragic irony, isn't it? The clotting system, meant to save us, can turn into an internal blockade starving tissues. It's like your emergency response system accidentally setting up roadblocks on the escape routes.
Okay, so we've seen the crisis inside the cell, the body's kind of frantic stress response. How does this translate to the bigger picture, like managing blood flow and pressure across the whole system?
Right, so this brings us to the body's wider vascular responses. Locally, in tissues, there's something called autoregulation. Tissues can sort of manage their own blood flow by releasing biochemical mediators like those cytokines we mentioned.
Little chemical messages.
Yeah, telling nearby blood vessels to either dilate, open up, or constrict, narrow down. That's local control. But systemically, maintaining overall blood pressure and perfusion relies on those three major components we talked about earlier working together: blood volume, the cardiac pump, and the vasculature.
Fluid, the pump, the pipes.
Exactly. And there's a key equation that connects them. Mean arterial BP equals cardiac output x peripheral resistance.
Okay, break that down. Mean arterial BP, that's average blood pressure.
Yeah, it's the average pressure pushing blood through your vessels over a full cardiac cycle. Cardiac output is how much blood your heart pumps per minute. It's your stroke volume, how much blood gets ejected with each beat times your heart rate. And peripheral resistance is basically how clamped down or relaxed your blood vessels are, especially the tiny ones called arterioles. Their diameter is the main factor there.
Okay, so that MAP number, the mean arterial pressure, is there like a critical threshold? A number of clinicians watch really closely.
Absolutely, that's the crucial one. The text highlights that tissue perfusion and organ perfusion depend on mean arterial pressure, MAP. And critically, MAP must exceed 65 millimeter HHG for cells to receive the oxygen and nutrients needed to metabolize energy in amounts sufficient to sustain life.
65. Below that, and cells are basically suffocating.
That's the danger zone, yeah. That MAP number you see on monitors in the hospital, it's not just data, it's literally the body's threshold for survival at that moment.
How did the body control that pressure? What are the mechanisms?
Okay, so there are primary, really fast-acting regulators. Think of baroreceptors. They're tiny pressure sensors located in the carotid sinus and the aortic arch.
And the neck and chest arteries.
Exactly. They constantly monitor blood pressure, blood volume, essentially. If they sense a drop, boom. They trigger the release of catecholamines, epinephrine, norepinephrine from the adrenal medulla.
Adrenaline rush.
Yep.
Fight or flight hormones. They immediately increase heart rate and cause vasoconstriction, clamping down vessels, trying to instantly bring BP back up. You also have chemoreceptors nearby, sensing oxygen and CO2 levels, which also influence BP and breathing rate.
So that's the immediate rapid response. What else?
Well, beyond that quick reaction, there are secondary, slower regulatory mechanisms. These take hours, maybe even days, to fully kick in. The kidneys are huge players here.
The kidneys.
Yeah. When they sense low blood flow or pressure, they release an enzyme called renin. Renin starts a whole cascade, ultimately producing something called angiotensin II.
I've heard of that. It's a vasoconstrictor.
A potent vasoconstrictor, really clamps down vessels, but angiotensin II does more. It also stimulates the adrenal cortex to release another hormone, aldosterone.
Aldosterone, what does that do?
Aldosterone tells the kidneys to hold on to sodium, and where sodium goes, water follows. So it promotes retention of sodium in water. This leads to hypernatremia, higher sodium concentration in the blood.
Okay, so holding on to salt and water. Right. And that hypernatremia then triggers another response. It stimulates the pituitary gland to release antidiuretic hormone, ADH.
Antidiuretic, so it stops you from peeing.
Pretty much. ADH tells the kidneys to retain even more water. The whole goal of this slower kidney hormone system is to increase the overall blood volume, trying to raise blood pressure back up over the medium to long term.
Wow. It's just, it's an incredible network of systems all interacting, isn't it? Baroreceptors, chemoreceptors, hormones like adrenaline, angiotensin, aldosterone, ADH.
Yeah.
All trying to keep that pressure above 65.
It's truly complex, each system trying to compensate, sometimes, as we saw with clotting, creating new issues in the process.
So today, we've really plunged into the deep end of the body's response to shock. We've gone from the tiniest cell struggling for ATP all the way up to the big circulatory system and all its controls. It really highlights just how intricate and interconnected everything is, working nonstop to keep us going, even when things go terribly wrong.
It really does. And grasping these processes, understanding that delicate balance and how easily it can be broken, leading to such devastating outcomes. It underscores why understanding this pathophysiology is so critical, especially for early recognition and treatment. In critical care, you often hear people say the body can become its own worst enemy in severe shock. Well, it's humbling to see how desperately it tries to save itself. But sometimes those very efforts can unintentionally speed up its decline.
So thinking about this astonishing array of compensatory mechanisms the body has, all these checks and balances designed to maintain perfusion.
Yeah.
What does it really tell us about that fine line between resilience and, well, vulnerability, right at the core of our biology, especially when something helpful, like you mentioned with the clotting cascade, can flip into a harmful positive feedback loop and just spiral things downwards. Something to think about.
Definitely something to think about.
We want to thank you for joining us on this deep dive today.